Hello everyone, this is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics Online. And this week we're going to be talking about Chapter 15, the chi-square statistic, which is both the goodness of fit statistic and the chi-square test of independence. So in this chapter, we're going to be talking about when a chi-square test is appropriate to use, and that's mainly with nominal and ordinal type data. We're going to test hypotheses about the shapes of distribution using the chi-square test. So basically, if we think that the population has a certain makeup, a certain percentage of the population is white, certain percent of the population is black, certain percentage of the population is Asian, Hispanic, et cetera, we can then test to see if the sample fits with that prior data based on the population data or based on a you know, prior sample that we took, right? We want to see if is our sample a good fit of what we know about the people we're studying. We can also test the relationship between two variables that are measured on nominal or an ordinal scale. This is mainly used, I should say, with nominal variables. So if I have two nominal variables and I want to see if there's a relationship between them, if there's a contingency, then I can use the chi-square test of independence. And after I do the chi-square test of independence, it just tells me whether or not the variables are related, or there's no relationships, or are they, dependent on each other, or are they independent? And if you reject the null hypothesis, you could then calculate a measure of association, like a correlation, basically. And this comes in the form of a phi coefficient, or in a bigger problem where you have more than a 2 by 2 table, you can then calculate something called Kramer's V. This is like a correlation, basically, for nominal variables. So we call the chi-square test a non-parametric test because we're not looking at means and standard deviations. We're also not relying on assumptions. So we're not talking about normality. We're not talking about homogeneity of variance. So we're basically threw everything out. We don't need mean, standard deviations. We don't need assumptions. These are distribution-free tests. And that's why they're important, because sometimes we can't meet the assumptions. Think for instance using frequency data, nominal variables. You can't calculate means of nominal variables. You can't calculate standard deviations of nominal variables. So how would you ever test it in a conventional format? So you can't use t-test, can't use ANOVA, and you certainly can't use Pearson correlation, right? Pearson R. So we need an alternative, and we need a test that does not require us to have, parameters or to estimate parameters of the population, and that we don't need to calculate means and variances and all that stuff with, and that's what the chi-square test does. So it's a good test for nominal data. It's also a good test when you have interval or ratio data, but you fail to meet the assumptions. Let's say your homogeneity of variance assumption was way off. I mean, instead of running the ANOVA or running the t-test, you can do an alternative, a non-parametric alternative to it. The problem with that, though, is that these non-parametric tests like chi-square, these tests are low in power, low in statistical power. So if you're trying to reject the null hypothesis and you're using a non-parametric test, you're putting yourself at a big disadvantage. So my rule of thumb is you never want to use a non-parametric test unless A, your data is nominal, like frequencies, right? Then you have no choice but to use chi-square. Or B, you've completely obliterated the assumptions. Like you're not even close to meeting the assumptions. Because if you're in any way remotely close to satisfying the assumptions for a t-test and an ANOVA, you want to use those tests because they're more powerful than, say, using the non-parametric equivalent. And there are non-parametric equivalents for ANOVA and a t-test. You have something called the binomial test or the sign test, which is like the equivalent of a t-test. That's a non-parametric equivalent. Uh, you have also the same thing for ANOVAs. So there's something called the Kruskal-Wallis ANOVA. That's a non-parametric equivalent of ANOVA. There's a bunch of other ones too, but they're relatively weak. So don't use them unless you have no other choice. Or you have nominal data, then you have to use chi-square. So as I mentioned, these are distribution-free tests. Um, Most of the time, participants are classified into categories. So this is mainly nominal data. You could use ordinal or ranked data too, but since you have the option of using like Spearman's row correlation with ordinal data, then that might be an alternative to use. And you would rather use Spearman's row if you have ordinal data and you want to find association between ordinal variables. But if you have nominal data, you definitely have to use chi-square. If you have interval or ratio scale data, you need to use t-test, ANOVA, correlation, etc. Because those are going to give you more information. Those are a more powerful test, statistically powerful test. Those are better tests to use. But if you don't have it, then you're stuck with the non-parametric equivalent, right? So the first test I want to talk about, and I did mention all those other tests that we're not going to get into, but they're out there if you want to look them up. Yeah, the first test we're going to talk about is chi-square goodness of fit test. Excuse me. Sorry about that. Been pretty sick the last week. The goodness of fits test is I'm looking at my sample to test hypotheses about proportions in the population. So I want to say, does my sample fit with what we know about the population in terms of proportions? Proportions are based off of frequencies. So if in the population, 60% of the population is female and 40% is male, let's say I know that, and I gather a sample, and I want to see if this sample is going to fit with what I know about the population, or is this sample different from the population? And maybe I do this to see, is the population changing? So you can look at like year after year, you can actually look at population change. And you can then, compare through a chi-square what do I have now in my sample, proportions of males and females, and what do I have in my population? And is it different? Has the population changed since last year? And there's more complicated ways of doing this, but this is a very basic way of doing it. And I could do that year after year after year, or I could do it decade after decade. It depends on what kind of research you're interested in, right? Or I can look at preference that changes over time in terms of, favorite potato chip. So here are my 3 brands of potato chips. Based on previous research, we know that 52% likes brand X, 48% likes brand Y. Has it changed? Maybe you instituted a marketing campaign for brand Y, and you want to make brand Y more popular, and so now you're looking at take the chi-square and you say it's different than what it was originally reported. So there has been a change. So when you're looking at preference, or you're looking at sort of the way things were, the proportion in the population, the status quo, when you want to see if there's a change, that goodness of fit test for chi-square is an effective measure. So here's 40 students, and I can depict the 40 students' grades in various ways. You have a bar graph on the left. You have this basically frequency chart in the middle. And then you have the cells, outline the cells on the right. So chi-square is going to make use of the cells. So the format that you see all the way to the right is the format that we're going to calculate chi-square. These values are called the observed values. Those are what we have in our sample. We're going to then compare them to the expected values under the null hypothesis. So basically, this is what we have. Now, how many A's, B's, C, D's, and F's would we expect under the null hypothesis. And the null hypothesis could be basically anything. It could be that we expect an equal number of A's, B's, C's, D's, and F's, right? So that's one version of the null hypothesis. It could also be that previous classes had these percentages of A, B, C, D, and F, and I want to see if my class of 40 students is different than previous classes. So these are my sample. What you see written here is the sample data, and then we have to compare it to the expected values under the null hypothesis, and then we're going to see if there's a difference. So the null hypothesis could be equal proportions. That's one common one. That if you just want to look for preference, you're going to use the null hypothesis of equal proportions. For example, let's say you're doing Coke versus Pepsi, like the blind taste test, blind challenge, Coke versus Pepsi. And you want to see, is there a preference? And so you pour Coke and you pour Pepsi into 2 cups, right? And you can randomly assign whether the cup's on the right or the left. So the order in which the cups are presented, you could, if you think that's going to bias their opinions or their preferences, which I don't think it would, but you could mix up the cups and put Pepsi on the right first and then move Coke on the right afterwards. You do all that stuff to keep it all fair. And so the null hypothesis for preference would be that people prefer Coke and Pepsi the same. There's no difference in preference. 50% of the people are going to pick Coke, 50% of the people are going to pick Pepsi. And then you gather a whole bunch of people. Let's say you get 100 people, and they taste both of them. And like I said, you can counterbalance the order. You put the Coke first for one person, the next person gets Pepsi first. So there's no order effect. And then you have them make a decision. Which one do you like better? And so we tally up those 100 people, whether they like Coke or Pepsi better, and we compare it to the expected value, the expected frequencies under the null hypothesis, which says that they prefer them both equally. 50% say Coke, 50% say Pepsi. If I have 100 people in my sample, then exactly 50 people want Coke, 50 people want Pepsi. If I have 500 people in my sample, then 250 people want Coke, 250 people want Pepsi under the null hypothesis that says that there's no preference. They're equal. And then I compare the actual sample and what they prefer to the expected value under the null hypothesis, which was 50-50. And then if you extend it to 3 categories, it's going to be 1/3, 1/3, 1/3. If you had 4 different choices, it would be 1/4, 1/4, 1/4, 1/4, right? 25% for the 4 choices. So it's the number of choices, 100 divided by the number of choices, if there's no preference, which is a very common way to run the chi-square goodness of fit test. The alternative just says that there is a difference. They're not equally spread out over the number of choices. So in the case of the Pepsi and the Coke example, it's not 50-50. There clearly is a preference. And that's the alternative. So the null says there's no preference for the goodness of fit test. The alternative says there is a preference. This is a very common problem that you see in the chi-square literature. You could also have a goodness of fit test that looks at proportions. So like the A, B, C, D, and F grades, right? So based on previous classes, 10% of people got A's, 20% got B's, 30% got C's, 20% got D's, and the rest got F's. So I have proportions based on previous classes. I can then gather my sample this semester's classes, and then I can compare it. And is this semester different than, what the grade distribution in the past? So the null hypothesis would be the grade distribution that happened previously over many years, or maybe it's last year. Could be averaged out over many years, could be last year, it doesn't matter. it is what you set it to be, right? If you're interested in seeing, is my class different than last year, then use last year as a null hypothesis. Is my class different than the average of all my classes, then use the average of all your classes as the null hypothesis. And you compare the sample, this year's proportions of grades, A, B, C, D's, and F's, to last year or the average of previous years, whatever you want to do. And that's all you have to do is you're going to compare the counts in the sample to what we'd expect if the null was true. And if our counts in our sample deviate greatly from what we would expect if the null is true, that means my chi-square statistic will get larger, and I'll be able to reject the null hypothesis. And that is the goal almost always for chi-square, unless you're doing model fitting, which we're not going to talk about. If you're doing model fitting, then you don't want to reject the chi-square. But other than model fitting, you want to reject the chi-square to say that there is a difference. Or maybe you're interested if there is no difference. But the alternative is that there is a difference. The null is that the proportions are the same as what they were previously, or they're equal proportions in the case of preference. So as I mentioned, everybody is counted once. So in the Coke Pepsi challenge, you could either pick Coke or you could pick Pepsi. You can't pick both. So there's independence of observations. You can only be in one category. That's important. Other than that, the other caveat would be that the expected value in each cell, in each group, should be greater than or equal to 5. And the book talks about this, that you have to have expected values. So under the null hypothesis, you should expect at least 5 people in each group, in each cell. If you don't have that, if you have less than that, then chi-square is going to be a mess. You don't want to use chi-square then. You can try to use something called Fisher's exact test, but we're not going to talk about that, but it's like an alternative chi-square. If you have less than 5 expected frequencies in each cell. So as previously mentioned, because I can't keep, I always go ahead because I digress and I get into something and I'll kind of like do like coming attractions. I'll like lecture the whole lecture in one slide, which is always challenging to try to slow myself down here. So I apologize for that. Expected frequencies are what you would expect of the null hypothesis. So 50-50, the expected frequency would be 50% times the total sample size. So all you have to do is multiply the expected frequency in each cell, that's basically represents the null hypothesis, times your sample size, and that'll give you the expected number of people. So if it's 50-50, then it's 50% times the sample size. If it's 25%, it's 25% times the sample size, and that gives you the actual number of expected people. Now, the difference between the observed people, the people actually in your sample, and the expected values in each cell is that the observed people are always integers. They're always whole numbers, and they're always positive, not zero, I should say. I mean not non-zero. Zero or positive numbers, integers, whole numbers. So you can only have like 2 people in a cell, 3 people in a cell, 0 people in a cell. You cannot have an observed frequency of like 3.15. You can't have 3.15 people in one group. Doesn't, unless you're going to slice people up, which we're not going to do. You have to have whole numbers. The expected value, though, can be fractional. So that's important to know. You can have an expected value in each cell that's fractional, but the observed value in each cell has to be a whole number. And here is the chi-square statistic. It looks like a fancy looking x squared. That's the chi-squared. It's equal to the sum of f sub o is the observed frequency minus f sub e is the expected frequency squared over f sub e, the expected frequency. So it's observed minus expected, square that, divided by expected. And the reason why you divide by expected is because you're weighting it. And if you have smaller expected values, then any deviation from the expected value is going to be weighted more than if you have larger expected values. And that's why I said you can't have expected values less than 5, because then the weighting gets really out of control. But it's observed minus expected in each cell, square it, square the difference, so you're going to get a positive number. So chi-square can only be, it could be 0 or it could be positive. It has to be non-negative, right? You cannot have any negative values of chi-square. It's a positively skewed distribution, kind of similar to F, but it changes depending on the degrees of freedom. It changes pretty radically. But chi-square is always observed minus expected squared over expected, and then sum that up. For each cell, you're going to add them together. So you compute this formula for each cell, and then when you add them together, you get your total chi-square. And then you have to determine whether it's significant or not. It has to be positive. It has to be positive or 0, right? And it's a positively skewed distribution, the chi-square distribution. So the null hypothesis is not rejected when the discrepancy between the observed and the expected values is small. So if your observed is very close to your expected, you're not going to reject chi-square. You're not going to reject the null for chi-square. That means you're not going to find a significant chi-square. But when the discrepancy is large, you're going to find significant chi-squares. So when the null is true, the chi-squared value should be relatively small. When you reject the null, the chi-square value should be much higher, right? And then you have to compare your chi-squared value to your degrees of freedom. Degrees of freedom are equal to the number of categories, or number of cells in this case, for goodness of fit test. Number of categories minus 1. And there's a different critical value for each degree of freedom, and then different ones for the alpha value, 0.05 versus 0.01. And this is what chi-squared looks like. Kind of looks like F, right? F distribution looks very similar, positively skewed. However, this distribution will change depending on the degrees of freedom, right? It'll shift. The peak of the curve will shift to the right, depending on the degrees of freedom. And your obtained chi-square statistic has to fall in the critical region. And the critical region is given in the appendix for chi-square. So you have to look up the degrees of freedom, you have to look up the alpha value, and then it will give you the critical region for chi-square. And then if your obtained chi-square is greater than the critical value for chi-square, you're going to reject the null. So it's very similar to doing what you did with the F test, the ANOVA. If it's greater than the critical value, you reject. It's a one-tailed test. There's no negative values, so you don't have to worry about directional, non-directional. There's no such thing. It's just a one-tailed test. So you determine the significance level, 0.05 usually. You find the critical value in the table based on degrees of freedom, and then you compare. It's as simple as that. Here's what the distribution looks like for degrees of freedom of 3. That means you have 4 categories. So if your degrees of freedom is 3 here, you have 4 cells or 4 categories. And at 0.05, the chi-square value is pretty high, 7.81. So it's out in the tail, pretty far in the tail. It can get even higher than this. It can get really, really high, especially with small samples. You can get, the thing with chi-squares is very susceptible to the sample size. So when your sample size is large, it's very easy to reject the null. So you have to be very careful about interpreting chi-square when the sample size is large, because it gets pushed towards significance really quickly. So what I like to do is I like to look at the effect size also when we're doing chi-square, because that gives me a measure that's independent of sample size. If you're reporting the chi-square statistic, you're going to write the chi-square, like the fancy x square here, parentheses 3, which means there's 3 degrees of freedom, which means there's 4 categories, and then give the sample size, because that can affect significance. And that equals 8.08, and if that's your obtained value, 8.08, it's greater than the critical value, so you will reject the null. P is less than 0.05. And that basically means that there is a difference or there is a preference. As previously mentioned, you want to use chi-square with nominal data. If you have interval or ratio scale data, conduct a t-test, conduct a correlation, conduct an ANOVA. Don't bother with chi-square or any non-parametric test because the statistical power is weak. So if you have a choice between using chi-square versus using t-test or ANOVA, you're going to use t-test or ANOVA. You only want to use chi-square when you have naturally occurring nominal variables. So it's very easy to like make your variable into a nominal variable. For example, I give you a scale of depression and you get a score from 0 to 100. That's a interval scale measure. You can do t-test, you can do ANOVA with that, you can do correlation, right? However, let's say that I decide to break that scale from 0 into 100 up into low and high. So I classify you as having a low level of depression or a high level of depression. Now I've taken that continuous variable, I made it discrete. I've taken that interval level of measurement and I've made it into nominal. So now I can use chi-square. The problem is that you kind of wreck the measurement. You're losing information. By turning an interval level variable into a nominal level variable, you're throwing away information. And you should never do that. And unfortunately, people do this. They do this especially when they want to run between groups factors in ANOVA. They take a continuous variable and they basically make it into like a high-low. You know, they do what's called a median split. And they make it into a nominal variable. And that is a bad practice. So only use chi-square when you have naturally occurring nominal data. Do not make a continuous variable into a nominal variable. That's bad practice. Let's look at this learning check. The expected frequencies in a chi-square test, while they're not always whole numbers, can they contain fractions or decimal values? Can they contain both positive and negative values? And can contain fractions and negative values. So we know that chi-square is always positive. You know that expected frequency cannot be negative. You can't expect -3 people to be in this group. There's no such thing as -3 people. So there's no negative values. So that gets rid of all the negative values, and you know it can be fractional. So that leaves only one answer, and the answer is B. The expected value can contain decimals or fractions. It has to be positive or 0. The observed value cannot contain fractions or decimals, only the expected values. Let's look at the second one here. In a chi-square test, the observed frequencies are always whole numbers. Sounds pretty normal. A large value for chi-square will tend to retain the null hypothesis. Well, we know that observed frequencies have to be whole numbers. So there cannot be any fractional values. And we also know that a larger chi-square means it's easier to reject the null hypothesis. And basically, that means larger values are good for rejecting the null hypothesis. Now we're going to move into the second form of chi-square called the chi-square test of independence. And this looks at a relationship between two variables that are both measured on a nominal scale. So think of this as like a correlation between two nominal variables or two categorical variables. Each individual is classified on each variable, right? So if there's two variables, each person has a score on each of the two variables, and then they fit into one cell. And the cells represent the interaction between the variables. It's called the contingency table. And the data is purely frequency. So let's say I wanted to look at, is there a relationship between your gender and if you're an alcoholic? Those are two nominal variables. Gender, let's say for simplicity's sakes, let's leave it at male, female, although some people will argue that we should include non-binary as a choice. We can leave it at male, female for the example. And alcoholism, we'll leave it at yes, no, just to make it 2 by 2. So each person that's in those 4 cells, right? There's 4 cells. You have male, female. That's one variable with 2 levels. So that's 2 levels. And then you have alcohol, non-alcohol. So that's another variable with 2 levels. So 2 levels times 2 levels gives me 4 cells in total. And each person in your sample is going to go into one of those 4 cells only. They have to pick one of those 4 cells. So if they're male and then they're alcoholic, they go into the male alcoholic cell. If they're a male and they're non-alcoholic, they go into the male non-alcoholic cell. If they're a female and alcoholic, they go into the female alcoholic cell. And if they're a female and non-alcoholic, they go into the female non-alcoholic cell. And now I can compute the chi-square to determine, is there a relationship between these two variables? Is there a relationship between gender and alcoholism? The null hypothesis says they're independent. The alternative hypothesis says they are related. Are they independent of each other? That's the null. There's no relationship. Another way of saying this is the correlation is 0 between these variables. Although this is not technically a correlation, it's chi-square. But you can make a correlation out of this later on. So is there a relationship or not? The null says there's no relationship. The alternative, the research hypothesis says there is a relationship. Variables are considered independent if you fail to reject the null hypothesis. That means they don't go together. Once again, just like the goodness of fit test, we have to calculate observed frequencies and expected frequencies. Based on the null hypothesis, we calculate the expected frequencies. The expected frequency is simply related to the row and the column. So to find the expected frequency in the chi-square test of independence, I have to first find the row totals and the column totals. So all I have to do is add up the observed values over rows, add up the observed values over the columns. So I should have row totals and column totals, and I should have a total sample size. So when I add up the rows and I add up the columns, I should get the same number, which is your sample size, which is n. And then I can compute the expected frequencies based on those row totals, the column totals, and the sample size. So the expected frequency for each cell is the column total times the row total for that cell, right? So each cell belongs in one row and each cell belongs in one column. So you find the row total for that cell, you find the column total for that cell, you multiply them together, and you divide by the total sample size. And that gives you the expected frequency, expected value for that cell. So once you calculate the row totals and the column totals and you have the sample size, you can then easily find the expected values. Row total times column total divided by n. And you do that for each cell. So here, if I have a 2 by 2, gender and alcoholism, I have 4 cells. But I could have much bigger problems, right? I mean, I can have ethnicity, which has probably 8 or 10 different categories, by grade received in a class, which has 5 categories. So if I have 10 ethnicities and 5 different grades, now I have 50 cells. Now that's going to be that's going to be really rough to calculate. And if I have 50 cells, it's going to be problematic unless my sample size is huge. Because remember, I want my expected value in each cell has to be greater than or equal to 5. And if I have a lot of cells and not many people in my sample, I'm going to have really small expected values. And if it's less than 5, I can't use chi-square. So if you have a smaller sample, you don't want that many cells. You know, a 2 by 2 chart contingency table for chi-square is probably the best way to go with a small sample. Because the more cells you have, the more sample you need. And then I find chi-square the same way I did with the goodness of fit test. So it's going to be observed minus expected squared over expected. So each cell, you're going to do this formula for each single cell, and then add up all those values to get a total chi-square. Observed minus expected squared over expected for each cell. That'll give me the chi-square value when I add them all up. If I have 4 cells, then I have 4 values to add up. If I have 50 cells, then I have 50 values to add up. And it's going to be messy. And then my degrees of freedom is going to be equal to the number of rows minus 1 times the number of columns minus 1. So in the case of 2 by 2, I have 1 row. I have 2 rows and 2 columns. So number of rows minus 1 is 1. Number of columns minus 1 is 1. 1 times 1 is 1. So I'd have 1 degree of freedom for a 2 by 2. It's always going to be number of rows minus 1 times number of columns minus 1 for your degrees of freedom. So as previously mentioned, chi-square can be used to look at the association between variables. If you have interval or ratio variables, don't use chi-square test of independence. Use Pearson R. It's a much better test. So if you have interval or ratio, use Pearson R. If you have ordinal, don't use chi-square. Use Spearman's rho correlation. If you have nominal and nominal, now use chi-square test of independence. Because it's the only thing you can't use any of the others. But if you can use something else, use something else. Chi-square should only be reserved really for nominal variables. Now, we can find a relationship similar to what we found in terms of effect size with the t-test and with the ANOVA. Remember with the t-test, we had Cohen's d as a measure of effect size. With the ANOVA, we had eta squared as a measure of effect size. With correlation, we had r squared as a measure of effect size. So you have something similar for chi-square as a measure of effect size, depending on which test you're using. A significant chi-square means that the null hypothesis should be rejected and there's no difference in the case of goodness of fit, and there's no relationship in the case of test of independence. But this does not tell us the size of the effect. So If we reject the null and we say that there is a difference or that there is a relationship between two nominal variables, we know that they go together or there's a difference. We don't know how big the effect is, so we need a measure of effect size. And so for the goodness of fit test, we're going to use something called Cohen's W. Cohen's W involves the use of proportions. So you have to convert everything into a proportion. So basically you take each frequency and you divide it by the sample size. So in each cell, you're going to take the frequency and divide it by the sample size, the total sample size, and that gives you a proportion, a decimal, proportion of the decimal. And you're going to do proportions for the observed, and you're going to do proportions for the expected. Remember that the expected n, the sample size for expected, is the same as the sample size for observed. So it's over the same n. But you have to convert the observed into a decimal, the expected into a decimal, and then do observed minus expected squared over expected. So you have to get rid of the whole numbers and turn them all into decimals. And then you have to sum it up. Each cell, you have to do this for each cell, sum it all up, and then take the square root. And they get you something called Cohen's W, which I don't personally use very much. But if you're using goodness of fit test, it's one way to figure out how strong the effect is. I rarely run goodness of fit test. I run mainly test of independence to look for relationships. But I guess if you were running and you were looking at preference or you were looking at change in population proportions over time, you would be running goodness of fit test. Cohen suggests that 0.10 is a small effect. So this is similar to Cohen's D. 0.10 is a small effect, 0.30 is a medium effect, 0.50 is a large effect. And since it's a measure of effect size, sample size does not play a role in calculating W. Now, W can be calculated much easier than looking at proportions. You can actually calculate W using chi-square statistic. So if you had the chi-square already, you can then calculate W that way. But you can also calculate it with proportions. You can also calculate W by calculating the phi coefficient. So the formula is basically the same. The only difference is that if you're doing a goodness of fit test, phi and W are the same. It's a measure of effect size. But if you're doing the test of independence, phi means something more, basically. It's like a correlation. So if you're calculating an effect size for the chi-square test of independence, you don't want to calculate W. You want to calculate phi. And phi is equal to the square root of chi-squared over n. This is similar to a correlation between two nominal variables. And if you square phi, you'll get the equivalent of r squared. So you get the proportion of variance if you take the phi value and square it. Just like if you square r, you get the proportion of variance. You get the same thing with phi squared. So it's an alternative to correlation for nominal variables. Now, phi only works for 2 by 2. Let's leave it at that. If you have 2 by 2, you calculate phi. If you have anything bigger than a 2 by 2, then you can't use phi. You must use something called the Kramer's V. So Kramer's V is almost exactly the same formula as phi, except the denominator is a little bit different. Kramer's V is equal to the square root of chi squared over n divided by the degrees of freedom asterisk. Now the degrees of freedom asterisk is the smaller of the number of rows minus 1 or the number of columns minus 1. Since we're looking at a bigger than 2 by 2 table. So 2 by 2 table, phi. More than 2 by 2 table, you have to use Kramer's V. Interpretation is basically the same. It's a measure of the association. But you just have to alter the degrees of freedom in the bottom by the smaller of the number of rows minus 1 compared to the number of columns minus 1. This is a chart for interpreting Cramer's V. As you can see, the interpretation of Cohen's W is the same as the degrees of freedom of 1, because it's really the same thing. 0.10 for small, 0.30 for medium, 0.50 for large. Now, if the smallest dimension is 2, it has degrees of freedom of 2, which means there's either going to be 3 rows or 3 columns. Then it changes. So now the small effect goes, is decreased, the medium effect is decreased, and the large effect is decreased. So as you keep increasing the size of the table, contingency table, these values get smaller and smaller in terms of what to consider a small, medium, or large effect size. The assumptions of chi-square, they're independence of observation. So basically, you only can have one person in each cell. So you cannot have a person in multiple cells of the chi-square. That's what independence of observation is. And as I previously mentioned, the expected value in each cell should be greater than or equal to 5. Let's take a look at these questions. Basic assumption for a chi-square test is what? Normal distribution, interval or ratio scaled, independent observations, or none of the other choices or assumptions for chi-square. Well, we know normality is not. We know that we don't need to estimate any parameters. We know that interval or ratio shouldn't be use chi-square. Observations have to be independent, right? So you can only have one person in each cell, and therefore the answer is the observations must be independent. You can only have one person in each cell. As basic as that. That's the only assumption. And then the more advanced assumption is that the cell expected frequency is greater than or equal to 5. But the most basic assumption is independence of people in the cells. It can only be in one cell. Let's look at this problem. The value of degrees of freedom for a chi-square test does not depend on the sample size. And a positive value for the chi-square stat indicates a positive correlation. Now, sample size is not in the table. So if you look at chi-square, you're going to look up degrees of freedom, and you're going to look up the alpha value, whether it's 0.05 or 0.01. And you're not going to look up the sample size. So that's a difference. You don't need the sample size to find the critical value. And the second one, chi-square basically is testing that there is some kind of association, but it doesn't indicate a positive correlation at all. Remember that there's no negative chi-square value, so how can you talk about correlation when you have no negative values? And so that first one is obviously true. Chi-square test degrees of freedom only depends on number of rows minus 1 times the number of columns minus 1. Has nothing to do with sample size. And chi-square cannot be negative. So there's no point in using it as a correlation. That's the problem when you're looking at something like phi. Phi is showing an association. It's not showing you, positive or negative correlation. It's just saying these variables go together or they don't go together, right? And, you can see how strongly they go together, but you have no idea what direction those variables are going in. So once again, it comes back to one of the themes of this week's lecture, and that is that non-parametric tests are good when you have no other choice. Chi-square test is good because you have no other choice. You can't do anything else with nominal data other than chi-square. So chi-square is good. But if you have a choice, if you have a higher level of measurement than, say, nominal, then you want to use more advanced procedures or what are called parametric tests, including chi-square, t-test, ANOVA, Um, I mean, not chi-square, t-test, ANOVA, regression correlation, because that's going to provide you with much more information than chi-square or some other non-parametric test would provide you. And so parametric tests are better than non-parametric tests overall, if given a choice. They have more statistical power, which makes it easier to reject the null hypothesis. And there's so many other non-parametric tests out there. I can give like a whole class of non-parametric tests. There's so many of them. But really, you don't want to use them. Use chi-square, basically. I never use the other ones because they're just not good. It's a pretty simplistic analysis. The other ones aren't good. If you really violate the assumptions of normality and homogeneity of variance, I guess you could justify using them. But the good thing about these parametric tests and the assumptions are that they're very robust, and I keep using the word robust like every lecture. That means that you can violate the assumptions, and you're still okay unless you really severely violate them. Especially the case when you have equal size groups. So even if my variances were shown to be not equal with the F test to compare the variance, the F max test or Levine's test for variances, whatever you're using, you can generally still justify running the ANOVA. So you would need a complete, like it would have to be so severely off to not be able to run a parametric test. So my advice generally is if it's kind of in the same ballpark or the same universe, if it's kind of normal, if it's kind of the same variance, run the parametric test because you're going to get better results with the parametric test. And the assumptions will hold up because they've run all these simulations and show that even with severe violations of the assumptions, you still get good data, good results out of the parametric test that will hold to the population that you're studying. So hopefully it's not too complex. I think it's a lot easier to understand than the factorial ANOVA and all that stuff. That's a little bit more, there's a lot of information there. So this is pretty basic. I think with a little practice, so go practice it, go online into MindTap, practice the problems, do some of the problems in the book. I will get the problems ready for the exam, and there'll be a review sheet for the exam, and then you can practice on your own. And I'm not going to give you anything that tricky. So I know it's an online class. It's a very difficult situation. If I had you in person, my expectations would be much higher, which might be a good thing for some people taking the class, that my expectations are fairly moderate. But I understand everybody's situation and the situation we're in. So hopefully that helps. If you have any questions, email me, make an appointment during my office hours, or just reach out to me in general. I can work with you if you can't make certain times. And I can even work through a problem or whatever with you if you need it. So just let me know. Bye for now. See you for the final exam.